So the operation I'm going to do next is I'm going to take row 2 and I'm going to subtract it from row 3. So the notation that I'm going to use, I'm actually going to write down row 3 first with an arrow pointing to it, because that just says row 3 is the one that's changing and being overwritten. And it's going to be overwritten with row 3 minus row 2. Okay, so that's what it means to subtract row 2 from row 3. Okay, so let's see what happens. I'm not going to do any other row operations. I'm just going to do that one. So right off the bat, notice that row 1 and row 2 are not going to change. So you can just copy those down before you begin, and you're not going to make any changes. Okay, so it's just row 3 that's changing. Okay, so let's perform this subtraction. So row 2 is being subtracted from row 3. So we're going to have 0 minus 0 for the first entry. That's just going to be 0. Then we'll have 3 minus 2 for the second entry, which is a 1. Now for the third entry, we've got negative 11 minus negative 7. Now be careful when you've got these double negatives. This is an easy place to make mistakes. And you might find it useful to have some scrap paper handy where you can just jot down rough work. It's worth taking your time to do things carefully, because as you might be able to guess, these problems take a long time to work out. So if you make a mistake somewhere, you may have to change, to go back and fix it may take a lot of effort, and sometimes you might even just have to start over. So in order to avoid that, do everything you can to be as careful as possible. But just be careful here. So what's going to happen? Negative 11 minus negative 7, that's like negative 11 plus 7, right? So negative 11 plus 7 is going to end up giving us negative 4. Okay, and then what about the last entry? So we got negative 27 minus negative 17. Same sort of thing, right? So it's actually going to be negative 27 plus 17. So that's going to give us negative 10. Okay, so now what am I going to do? Now I'm going to do 2 more row operations. I'm going to change row 1. I'm going to subtract row 3 from it. So I'm going to take row 1 and go row 1 minus row 3. And then I'm going to take row 2 and replace it with row 2 minus 2 row 3. So I'm taking row 3 and I'm subtracting it from both of the other rows, but in the case of row 2, I'm doing it twice. What I'm trying to do here is I'm trying to turn this into a 0 and turn this into a 0. That's how these row operations were chosen. Okay, so what's going to happen? Well, start by looking at what's not going to change. The only row that's not changing here is row 3. So I'm going to start by just jotting that down. 0, 1, negative 4, negative 10. And then let's now fill in rows 1 and row 2. So row 1, we're subtracting row 3. So we've got 1 minus 0. That's just going to give us a 1. Then we're going to have 1 minus 1. That's going to give us 0. Then we've got 2 minus negative 4. So that's like 2 plus 4, right, which will give us 6. And then lastly, we'll have 9 minus negative 10. So that's like 9 plus 10, which will be 19. So that's going to be a 19 here. So that's the first row operation. Now let's perform this second row operation. So we're going to take row 2 and subtract row 3 twice. Okay, so for the first entry, we're going to have 0 minus 2 times 0, which is just 0 minus 0. Then we're going to have 2 minus 2 times 1, which is just 2 minus 2, which is 0. And then for the third entry, we're going to have negative 7 minus 2 times negative 4. So that's like minus 7 minus negative 8. Or again, there's that double negative. So it's really like minus 7 plus 8, which is actually going to give you positive 1. So we actually put a 1 here. Okay, and then what is our last calculation? We're going to have negative 17 minus 2 times negative 10. So that's actually going to be negative 17 plus 20, which is going to give us 3. Okay, so that's the end of that step. Now, I'm going to do 2 more row operations, actually 3 more, but on this step I'm going to do 2 operations. And what I'm going to do is I'm going to take row 1, and I'm going to replace it with row 1 minus 6 times row 2. The reason I'm doing that is because I want to turn this 6 into a 0. And by doing this, that'll happen. But then I also want to turn this negative 4 into a 0. So what I'm going to do is I'm going to take row 3 and I'm going to add row 2 4 times. So I'm going to take row 3 and replace it with row 3 plus 4, row 2. Okay, so that's the operations I'm going to do for this step. Okay, so what's going to happen? Well, row 2 is not changing, so why don't I write that down first? Okay, always write down the row that's not changing first, and that'll help you space things out. And now, okay, well, let's start with row 1. We're subtracting row 2 6 times. So we're going to have 1 minus 6 times 0, that's just 1. 0 minus 6 times 0, that's just 0 minus 0, which is 0. Then we have 6 minus 6 times 1, that's going to be 6 minus 6. 19 minus 6 times 3, that's like 19 minus 18, which is going to give us 1. And that completes the first row. Okay, so next we want to do the second row operation. We're going to take row 3 and add row 2 4 times. Okay, so what's that going to look like? So row 3 is, okay, 0 plus 4 times 0 for the first entry. That's just 0 plus 0. The second entry, we're going to have 1 plus 4 times 0, which is just 1 plus 0. The third entry, we'll have negative 4 plus 4 times 1. That's just negative 4 plus positive 4, which is going to give us 0. And then for the constant term, we're going to have negative 10 plus 4 times 3, which is negative 10 plus 12, which works out to being positive 2. And you notice over here for our coefficients section, it's all just ones and zeros now. And I'm going to do one more operation, and then we're going to look at how to get a solution from here. I'm going to take row 2 and row 3 and just swap places. I'm going to interchange them. That's the other type of row operation we haven't done yet, but that's one thing we're allowed to do as well. And I'm going to go formally through what exactly you're allowed to do after this example. But for now, just know that you can't just do whatever you like. There are limitations. But this is the third type of row operation that you're allowed to do. And what's going to happen if we do that? Well, the first row is not changing, so it's just going to stay as 1, 0, 0, 1. The second and third rows will interchange, so we'll have 0, 1. This is the old row 3. It's now going to be row 2. And then the old row 2 is now going to be row 3. Okay, so that is about as simple as we're going to get. Now, here's the magic behind this method and why it works so well. What if I were to take this this augmented matrix and translate it back to a linear system? So, in other words, the first step we did where we started with a linear system and we transformed it into an augmented matrix, we're just going to do the opposite. We're going to go in the opposite direction. We have to note that the first column, that's the coefficients of the x variable in each equation. That's the second column is the coefficients of the variable y in each equation. And the third column is the coefficients of the variable z in each equation. And then, of course, these are the constant terms. So if we recover our linear system from that augmented matrix, what are we going to get? We're actually going to get, well, let me do it really formally here. We'll have 1 times x plus 0 times y plus 0 times z is equal to 1. That's the first equation. The second equation will be 0 times x plus, there's really a 1 here if I want to be really picky, but although you can see that doesn't change anything by adding it there. So we got the second equation of 0 times x plus 1 times y plus 0 times z is equal to 2. And then the third equation is 0 times x plus 0 times y plus 1 times z is equal to 3. That's the linear system that underlies this augmented matrix. And remember what I said, if you're looking at two systems, here's one, here's a linear system, and here's a linear system. Here's the idea behind this approach is that if we do these elementary row operations, these two systems are going to be equivalent, which means they have the same solution set. But here, this one that's moving around now, this one is much easier to solve. In fact, if we rewrite it so that the terms that have coefficients of 0 just aren't there, and I can skip writing the coefficients of 1 since they don't do anything, I really am going to get this. I'm going to get, in other words, this is going to be x equals 1, y equals 2, and z is equal to 3. So which of those two systems are easier to pick out the solution? This one or this one? Well, guess what? They have the same solutions, so we can just consider this one instead. And of course, the solution's right in your face, right? You don't even have to do any work if you're looking at this linear system. The work's already been done to get here. But that's the solution. X has to be 1, y has to be 2, and z has to be 3. So there's three different ways to write your solution. I mean, one of them is what we just have here. If I did a box around this and said that would be perfectly clear, right? I'm saying what x and y and z all have to be. But there's three other ways you can write your solution. I want to mention those right now. One of the ways is point form. So we can write, I can write them as a point with three coordinates. So the point consisting of the variables x, y, and z is got to be equal to 1, 2, and 3. That's the point form of a solution. I can also write my solution in what's called row form. So I'm just going to write square brackets. I'm going to write the variables, and I'll leave a nice amount of space in between. And I'm going to say that that's going to be equal to, and then I'll write the same sort of form, but over here I'll just write the actual values. That's the row form to express your solution. And then the other form that I want to consider is column form. So I'm going to do the same sort of thing, but I'm just going to arrange things vertically instead. So x, y, z as a column is going to be 1, 2, 3 as a column. So that's referred to as writing your solution in column form. Okay, so it's important to be familiar with all three of those. And of course, this one works as well. If all you're interested in doing is solving the system, there's nothing wrong with just writing it this way. But for now on, let's get in the habit, for reasons that will become clear later, let's get in the habit of using this form, column form, to express our solutions. It's just going to turn out to be so convenient for many different applications that we get into later. So for now, I won't tell you formally, I won't fully explain the reason why, but for now I'm just going to say we're going to stick with column form as a way to express our solution. Okay, a couple more comments I want to make. If we go back up here, back to this linear system, I mentioned that this is called the augmented matrix of the linear system. Well, there's two other things you can do. Well, there's lots of things you can do, but there's two other things I want to mention. You can just look at the coefficients if you want. So if I were to write down a matrix like this, so 1, 1, 2, 2, 4, -3. Remember, a matrix is just a 2D array of numbers. I'm going to do everything, but I'm just going to not worry about the constant terms. I'm just going to write down the coefficients. So that is the coefficient matrix. I don't have much room here, so I'm going to have to sneak it in on the side. So that's called the coefficient matrix. And then separately, I can look at the constant terms. So 9, 1, and 0. That's called the constant column, or sometimes you'll call it the constant vector. So let's write that down, is the constant column, or another name for it is the constant vector. It will be very convenient later to have access to this terminology, so let's make a point of adding it in right now. Okay, so that's called row reduction, and that's an efficient way to solve a linear system. If you have a lot of variables and a lot of equations, this is a much more efficient method than using the substitution method. And really what it's based off, it's really based off of the elimination method, which I didn't talk about, but that's also a method for solving systems that you should be familiar with from high school. Even if you've forgotten, don't worry about it. We're not going to use it directly, although we are going to use it, but we're going to use it in this form rather than in the form that you would have seen it in high school.